Okay, so some final thoughts for Module 6. Let's, of course, go through the least squares assumptions for multiple regression. Of course, we need some assumptions. We can't just run our models without thinking about them. So let's suppose we have our generic model with as many independent regressors as we want. In this case, it's up to k regressors. Assumption number 1 is the conditional distribution of u given the x's has mean 0. So this is the same as assumption number 1 from before. The expected value of u conditional on x is equal to 0. In other words, the variables contained in u, the things that are omitted from their regression, are uncorrelated with the x variables. If this is a problem if the omitted variable x2 belongs in the equation, or xk plus 1 belongs in the equation, so it is contained in u. So we're saying what's contained in u, xk plus 1, some additional regressor, is contained in u, and it's a problem if it's correlated with x2. This is the omitted, or sorry, if it's correlated with x1 or whatever variables we want in our model, and then if it's also a predictor of y1, then it leads to omitted variable bias. The solution is, if possible, include the omitted variables. Assumptions 2 and 3, the x's and y's are IID, independently and identically distributed. This is satisfied automatically if data are collected by simple random sampling. We're going to assume this is true for the most part in this class. Large outliers are rare. This is also satisfied automatically if data are collected by simple random sampling. Assumption number 4, no perfect multicollinearity. This one's a little different than what we had in the single variable model because it really didn't apply to the single variable model. This has to do with the covariance of your included regressors x1, x2, x3, etc. So perfect multicollinearity is when one regressor is an exact linear function of the other regressors. So if x1 is equal to 3 times x2, you can't include both x1 and x2. Perfect multicollinearity usually reflects mistakes in definitions of regressors or data oddities. If there's perfect multicollinearity, the statistical software will either crash, give you an error message, or drop the variables arbitrarily. The solution is just to leave one out. Leave either x1 or x2 out. Imperfect multicollinearity can be also a problem. Your variables are always going to be somewhat correlated. You never have perfect non-collinearity, right? You never have two variables where the covariance of x1 and x2 is exactly equal to 0. The problem is when you have covariance of x2 or x1 and x2 that's equal to maybe something like 0.95. They're highly correlated but not perfectly correlated. The problem is that including both means that maybe x2 is absorbing all the variation in x1 in your model, and so you really can't determine which one is the driving force behind the y variable. What this does is it results in large standard errors on beta of your. So if you had, y as a function of beta 1x plus x1 plus beta 2x2, and x1 and x2 are highly correlated, the standard errors on beta 1 and beta 2 are going to be really large, meaning that you fail to reject a null hypothesis on either x1 or x2. So the solution is just to leave one out. This is a common problem when you have dummy variables. So maybe in this case I'm defining student-teacher ratio large classes as greater than 20, and we'll define that as D1 is 0 if student-teacher ratio is greater than 20, and 1 if student-teacher ratio is less than or equal to 20, and then D2 is just the opposite, 1 if student-teacher ratio is greater than 20, and 0 if student-teacher ratios are less than or equal to 20. So if you include both of these in the model, they're perfectly correlated. So each time D1 equals 0, D2 equals 1, and vice versa. And this is a really common problem with dummy variables, especially with something like male and female dummies. You can't include both in the model. One has to be dropped. The sampling distributions. Again, why do we care about sampling distributions? Well, this follows from the least squares assumptions. The sampling distributions of the betas help us determine what distributions we need in order to determine statistical confidence. So under the four OLS assumptions from the previous slides, the exact finite sampling distribution of beta 1 hat has a mean of beta 1, the population value, and a variance of beta 1 hat, and it's inversely proportional to n. And this is the same for all other betas. This is nice because that means we can use the same statistical methodologies for all the betas in the model. And for large n, beta 1 hat is consistent, conditional on these four OLS assumptions holding. In other words, beta 1 hat converges in probability to beta 1. This is the law of large numbers. As n gets large, our estimate beta 1 hat gets closer and closer to beta 1, the population value, the probability trending towards 1. This also means that we can the beta 1 hat has an approximately normal distribution, and we can standardize this normal distribution by taking beta 1 hat minus its mean, and we know that this is usually the null hypothesis, beta 1 naught, over the standard error of beta 1 hat. And that gives us this expression here is our t-stat, right, which is normally distributed with mean 0 and variance 1. Same for all other betas, nothing new here, and this is really nice because this means that we can just use the standard z-table, and we can compare this value to the regular t-stat rejection rule, like reject if the absolute value of the t-stat is greater than or equal to 1.96, reject with 95% confidence.